Okay, hello everyone, and thank you very much for your positive feedback and all the comments that I receive about this series of videos about power system analysis. If you are watching this video, it's because you are interested in power system analysis, and I have been posting some videos about short circuit analysis. Specifically, the most recent videos related with unsymmetrical faults. Okay, this is the example. This is a practical example. This is one example regarding unsymmetrical faults, and this is, let's say, a continuation coming from the example 3.5. Okay. I highly suggest if you already finished the calculations using the example 3.5, okay, you are able, and I suggest to attempt this example. If you didn't finish or didn't attempt to solve the problem 3.5, please go back again and watch the video about the example 3.5 before attempting this. There are many reasons. One of them is there are many explanations over there about the short circuit contribution coming from the motor and the short circuit contribution coming from the generator. Okay. Um, in example 3.4, we study the double line to ground fault. Okay, that was the class. And in that example, we were interested on the contributions coming here from the generator. Well, some books they call the contribution coming from the transmission line, but to be honest, that contribution is coming from the generator. The generator is the device creating contribution here, and on the other side we have the contribution coming from the motor. Okay. Um, Again, don't attempt to solve the example 3.6. Don't jump the examples because you will need knowledge coming from the example 3.5. Okay. Example 3.5, it was very important that in those calculations we neglect the phase angle shift between the delta and star connection at the transformer. Okay, that was key in order to solve the problem 3.5, and now what we will do is overcome that issue, but by including the phase shift. Okay. Okay. Um, I already say to you, please attend 3.5 and then 3.6. Okay. What is the job today? The job today is we will start from the results that we create in example 3.5, and then what we want to do is include the appropriated changes in the calculations in order to consider the delta star transformer phase shift. Okay. Okay, let's jump. The first thing that you need to understand is in real life when we have a delta and star connections, transformers they can introduce a phase shift. That phase shift is coming from the delta and star connection. You must remember in real life delta and star connection they are a 30-degree relationship on currents. Okay. Of course, the square root 3 is also present in that relationship when we are using amps. But if we are working in the per unit system, the square root 3 disappear, and the main changes when you are moving from delta to star connection is the 30-degree. Okay. It's very important that you understand that calculating using the Thevenin equivalent model, they are not affected by the delta star transformer phase shift. Why not? Because we are imposing terminal conditions and the Thevenin model is the full equivalent model of the network, okay? But if we are interested on calculating any current or voltage inside the sequence network, we need to be careful, okay? If we are calculating, for instance, current contributions or yes, current contribution as we did in the example 3.6, these delta star connections, they can affect. But what you need to understand from now on is zero sequence, they are amazing because this delta star connection is not affecting the zero sequence components. But where is extremely important that you understand is that positive and negative sequence, they are affected by the delta and star connection at those transformers, okay? Okay, now what is the best way to consider the phase shift that is coming from delta star transformer? Well, what we need to do is modify the sequence networks, and specifically what we need to do is include a better model for the transformers in order to include the positive 30 degrees or negative 30 degree depending of the orientation and the sequence, including the phase shift inside the model, okay? All of you must remember that we can include that by making use of a very basic property. As you can see here, I have the system. This is bus bar 1, this is bus bar 3, and this is bus bar number 4, and this is bus bar number 2, okay? Okay, but coming back to my explanation, if you compare the positive sequence network here with the positive sequence network that I present in the example 3.1, there is a big difference. Here I am including a transformer, and this transformer is not modifying magnitudes. What I'm trying to say is the magnitude of the current IG1 in this side is the same magnitude on the other side. However, if you remember complex numbers, when we use this property, J 30 degree in this exponent over there, what it's doing is shifting by 30 degree the current from one side to the other side of the transformer. And that is what I need to do. What I need to do is that consider that the current that is coming from this side of the transformer, when it's moving from the delta to the star connection, we need to consider the 30 degree, and the best way to do it is including this phase shifting transformer. Okay? Is the same on the other side. However, we are not calculating any variable in this side, but again, between 1 and 3, there is a star delta connected transformer, and what I am doing is including a phase shifting transformer. There is no changes on the voltages or current amplitude, but there is a 30-degree change or rotation or shift when you move here, okay? And then we are doing something similar in the negative sequence, okay? In the negative sequence, what we are doing now is including the phase shift in the form of, again, a phase shift transformer, okay? Here you can see this is the positive sequence. You can see here the 30 degree and here the 30 degree. But in the other case, and we need to fix here something, When we are in negative sequence, the phase shift change, okay? It's clear that when you are moving in the negative sequence, we are changing by minus 30 degree, and we will say here, okay? Now, how these phase shifter transformers are affecting the calculations that we perform when we were working with the example number 3.5. Okay? Well, it's very simple to see. What we need to do here is extremely simple. Uh, Let me keep here, yes, the circuit model. Okay, what you need to think about now is that we are moving from one side to the other. And in this case, we are including a 30-degree positive angle shift at the generator contribution, okay? We are including plus 30 degree. The original current calculated in the example 3.5 was minus J 1.38. But because we are moving from the high voltage side to the low voltage side of this transformer, or in other words, we are moving from the delta star connected to the delta connected winding, what we need to do is include a phase angle positive 30 degree, and that means that this current will be leading by 30 degree the current from the star side. Now you must remember J is equivalent to 90 degree. Okay, in this case, this minus J is equivalent minus 90 plus 30. That is minus 60 degrees. Okay. On the other hand, if you look the contribution coming from the motor, you must be aware that because the current is not moving through any transformer, there is no phase shifting, and we will keep using the same current that we calculate and we obtain at the example 3.5. Okay? Then we will do the same now for the negative sequence. In the negative sequence now, what you need to understand is that there is again 30 degree, they are 30 degree angle shift between the star and the delta connection side of this transformer. But in this case, the current is lagging by 30 degree, okay? Now you can see that I am multiplying by minus 30 degree here, and this is the negative sequence current contribution coming from the generator, and we obtain this in the example 3.5 J 0.8. We multiply by this phase shift here is the same magnitude, but the angle, well, here there is 90 degree multiplying by of shifting the angle by minus 30, we obtain plus 60 degree. And all my students, they must realize that in negative sequence, again, this motor, the contribution coming from this motor is not moving through any transformer. As a consequence, the result that we obtain from the problem, or from the example 3.5, is still valid, minus J point 1.99. Okay. Now let's keep moving, and what we need to do now is to see what is the effect of including those new phase angle into the final solution of this problem. Okay, and the final step is that we will move from the positive, negative, and zero sequence word to the A, B, and C word. And what I am doing here is calculating the contribution on ABC coming from the generator using symmetrical components. And we are doing the same. We are doing that using the per unit system, and then we will calculate the same results using the amps. Okay, amps. Um, to calculate the amps is extremely simple. What we need to do is multiply by the base, and I clarify that the base was calculated in example 3.1, and also my students must remember that that current was calculated basically um, considering considering the 13.8 kV, the 13.8 kV area, because bus bar number 2 is located at that place. Okay, and now when we multiply the per unit values, um, we multiply the per unit values, and then um, we will obtain here the amps that represent the contribution coming from the generator. Okay. Right now is a very critical moment because my students are thinking, okay, we obtain here the results. We have that if we have the contribution coming from the generator, the phase A will be around 5 kilo amps. Then the phase B will be around 9.4, and the phase C will be around zero point 0.5 kiloamps. Okay, kiloamps. Yes. Um, but now the question is, what's happened if we compare those results with the example that we used before, and that was the sample 3.5. In the sample 3.5, we calculate all the contributions, remember, coming from the generator, coming from the motor, okay? And what I will do now is I want to compare the numerical results that we got from the example 3.5, and we want to compare that currents coming from the generator, uh, and see what is the changes that, including the effect of those phase shift has on the currents. Okay, what I will do now is I will introduce here below, and this is the example. Remember, these are the results coming from the example 3.5. Okay, and you can see here this is the current coming from A, B, and C. And you can see that in this case, the line A increased the current, and also the phase angle change, and also the phase B increase. But in the case of the phase C, the current decrease. Okay, and probably you are wondering what is happening there. Why we have these changes on the fault currents? Okay, well, the explanation is extremely simple. The situation is that the phase angle changes impose a different addition when those contributions arrive to the bus bar number 2. If you remember, the motor is not connected to any transformer. I mean, the current contribution coming from the motor is not affected by any phase shift. That is the reason also that we are not calculating the motor contribution, because there is no effect of any transformer phase shift. But the generator, phase angle, and magnitudes, they are changed because the current is moving through the delta star transformer. And here, that phase angle is affecting this transformation when we are moving from symmetrical components to ABC. Okay? Well, this is the last example. I hope you can understand clearly what is the impact of including the delta and start phase angle. And it's been a pleasure being here explaining this practical example. I hope you find useful, and thank you very much for taking time and watching the video. And this is all for this video. Thanks.